All right, so now we're doing activity 6 in lab 7, our RC circuits lab. In this activity, we're going to sketch a number of different graphs. All of the following questions refer to the charging case, that is when the switch has been on position B for a long time, and then at time equals 0, we switch it over, we flip the switch to position A. So we're going to run the simulation for the charging case once again, and we're going to pay attention to the charge on the capacitor plates. In particular, just after the switch is flipped to A, does the charge on the capacitor increase, decrease, or stay the same? And we've done this a couple of times already, so I guess I could go back and show it to you again. All right, so again, we're on B for a while, and then we flip the switch to A. We're going to watch that capacitor plate. Oh, I forgot to press to put on the display. So let's put on B again. Let's add to the display, and now let's flip our switch. And you can see that the charge on the capacitor is increasing. And then a long time after the switch is flipped to A, does the charge on the capacitor increase, decrease, or stay the same? So again, let's go back and take a look at that. All right, so it has now been a long time at A, and you can see that it is no longer changing the charge on the capacitor plates. Question 6.2. Use your answers to 6.1 to sketch the graph of Q versus T. So we know that just after the switch was flipped, that the charge was increasing on the capacitor, and that a long time later it was staying the same. So that means we're going to have something that has a steep vertical part to it at the beginning, but then becomes more horizontal towards the end. So that's going to look something like this. Okay. Use the relationship between Q and VC that you wrote in question 3.1 to draw a sketch of the VC versus T. So we know Q is equal to C times V, and so it's going to be proportional to it, and we just went through that exercise to see what that would look like. It'll look the same. The only difference will be what our asymptotic values are. And so over here, our asymptotic value is just going to be Q equals C times V of the battery. And here it's just going to be V of the battery. Use the relationship between VC and VR that you wrote in 3.3 to draw and sketch VR versus T. So in the charging up scenario, we know that the resistor voltage plus the capacitor voltage plus the battery have to add to be 0. So as the capacitor gains voltage, the resistor has to lose voltage. And so that one's going to be an additive inverse to that one. And it's going to look something like that one, where the high point again is going to be V battery and the low point is going to be 0. And based on this, what does the current as a function of time look like? The current is going to be V over R, so it's going to be the same shape. It's just going to have a different value, and that value is going to be V over R. Okay, let's go on to the next page. All right, same idea here, but this time for the discharging capacitor. So just after the switch is flipped to B, does the charge on the capacitor increase, decrease, or stay the same? Since it's discharging this time, it will decrease. A long time after the switch is flipped, does the charge on the capacitor increase, decrease, or stay the same? It will stay the same. Once it loses all its charge, it's going to stay that way. So this time we start with charge, but we end with no charge. And so again, this starts with C times the V of the battery and ends with 0. Use the relationship between Q and VC that we wrote to draw a sketch of VC. So again, it'll be the same shape, but now our biggest value is just the V of the battery. Okay, what's the relationship between VC and VR? VC and VR have to add to give us 0. So this time our VR is going to have to be the negative of what our VC looks like, where it has that same value, but it's on the negative side. And so our current will have that same shape again, but its value will be negative V over R. All right, third page for this activity. Does the slope of the Q versus T graph correspond to the I versus T graph for the charging case? So again, without having to flip back and forth, let me remind you that for the charging case, our Q versus T looked something like this. So we started out with a slope that was positive and big, and ended with a slope that was close to 0, but still a little bit positive. So this was our Q versus T case. What did our current versus time look like? Well, our current versus time started out large and ended up small. And so we had a current that looked like this. And so the slope here was positive and large, so that matches with this value of I here. And it ended positive but very close to 0, and that matches with what we see right here. So yes, it did correspond. Ooh, bad handwriting. Sorry about that. All right, well, what about the discharging case? So let's remind ourselves what our graphs look like for the discharging case. In the case of discharging, we said that our Q versus T graph started out fully charged. Oops, that's not right. Erase that, my bad. Started out fully charged and ended with no charge. And so our current versus time for our discharging case was negative, but had the same sort of shape. So as we look at the slope here we have a slope that is negative, very negative, and so we have a value here that is very negative. And here we have a negative slope that is very close to 0, and here we have a negative slope, negative value that is very close to 0. So once again, yes, that is true, that the slope, the slope of the Q versus T graph looked the same as the current. So there were no discrepancies. All right, question 6.12. How did the graphs you sketched compare to the graphs in the simulation? Discuss any discrepancies. So let's take a look at the simulation. And again, we have the address here. So we're going to take a look at this. All right, so this is for our charging case. This is our Q versus T, our V versus T, our VR versus T, and our current versus time, just like we expected. And if I switch over to our discharging case, there's our Q, there's our V, this is our VR, and that is our current. And all of these match what we had drawn in the lab.